Okay, in this video I'm going to cover some of the basics of friction forces. Alright, so the idea here is, let's consider a box sitting on a surface and we're going to apply a force P. Well, if the surface is completely smooth and doesn't have a way of generating any kind of opposing friction force, then the box is just going to slide. So there won't be a statics problem, it'll just be a dynamics problem. Okay, so what we're going to consider here is the case where it is a rough surface and we would model the forces with a free body diagram where we have frictional forces incorporated into the model. Okay, so here's a free body diagram. We have the weight moving down. Okay, so we know if I convert 100-pound mass to force, I have 100 pounds moving down. I have a normal force opposing the gravitational force. I have this pushing force P, and then I'm going to draw in a friction force. I'll call it Fs. Okay? So what we know about statics so far is that the sum of forces in the x direction is equal to 0, and the sum of forces in the y direction is equal to 0. So if this is a force P, and I'm looking at sum of forces x direction where to the right is positive, then I have that Fs, which is positive, minus P is equal to 0. So that would tell me that Fs is equal to P. All right, so Fs is this frictional force that I was talking about. Okay, so let's put a value to P. Let's say that P is equal to 40-pound force. Okay, then that would imply the frictional force is balancing this, and it's also 40-pound force. Okay, so what I want to add into this is what we know intuitively is that I can apply a force to this box, but if I push it hard enough, it's going to move. All right, so that implies, if you think it through, that implies there's a limit to this static friction force. All right, and it turns out that's true, that Fs max is going to be some coefficient mu. All right, so coefficient just means it's proportional to, and what we then look at is the normal force between, basically the box is exerting a force onto the surface, and it's not just the weight of the box, it's the angle of it matters. Because I have this set up as a horizontal problem, the surface is horizontal, the weight and the normal force are the same thing. So technically speaking, it should be the normal force times this coefficient of friction mu. All right, so I gave this in the problem statement that the coefficient of static friction in this case was, I put an S on it, mu s, is 0.7. So that tells me the maximum force that could be generated here. All right, so what is N? We know from sum of forces in the y direction equal to 0, where up is positive. We would have that N is equal to the weight. All right, and we know that the weight is 100-pound force. Okay, so plugging in, I know that mu s is 0.7, and I know the normal force is 100-pound force, and so our maximum opposing friction force is going to be 70 pounds in this case. So what would happen if I applied a pushing force of 80 pounds? Well, because 80 is bigger than 70, that would imply this box actually moves. Okay? All right, so that's the idea. You should know there are static friction forces and that they're not always equal to the maximum. One of the temptations is to plug into the formula Fs is equal to mu s times n. All right, that's only true if motion is about to happen. If you have impending motion, then the static forces are maxed out. Otherwise, it's just enough to counteract the pushing force Okay, so hopefully that'll make sense. We're going to talk more about this as we go through other examples.